In this video, we are going to look at the calculus of parametric equations. Let's start out with the derivatives. If I am given these two parametric equations where I have x minus 4 is equal to 5t and y plus 2 is equal to t, the first thing I could do is go ahead and write this back into the xy only and determine what I have in terms of a derivative. So I go ahead and I say, okay, well, if t equals y plus 2, then let's replace t here with y plus 2. And I end up with x minus 4 is equal to 5y minus 10. Solving for y, I get an equation of a line. These two parametric equations represent an equation of a line, which is y is equal to 1/5 x minus 16/5. Now we can see that if I were to take the derivative with respect to y, the dy dx, or the delta y over delta x, it's just going to be 1/5. Now, if I go back to my two equations and say, wait a minute, is there an easier way to do this? And the answer is yes. If I look at my two equations, my two parametric equations, and I solve for x, so I get x is equal to 5t plus 4 and y is equal to t minus 1. And I do the derivative of each one of these with respect to t, I'm going to get dx dt, which is 5, and dy dt, which is 1. Now, we know from calculus that dy dt divided by dx dt is dy dx. And you'll notice that if I put it back into just x and y, write it as a function of x, then a function of y in terms of x, then I can take the derivative and I get the exact same answers if I didn't have to go through that whole process. That is not a coincidence. Let's take a look at our first theorem. Our first theorem says, if I have two parametric equations where I've got the function x in terms of t and y in terms of t, then I can take the derivative of x with respect to t and the derivative of y with respect to t, provided, of course, the derivative of x with respect to t is not equal to 0. Then dy dx can be wrote as dy dt divided by dx dt, or in other words, y prime of t and x prime of t. So we can find critical points, just like we did when we first learned critical points in Calculus 1. We can find critical points using this definition of how we're going to find the derivative of a parametric equation. We're going to find extrema as well, and locations of intervals of an increase and a decrease, and inflection points and concavity. If you don't remember any of that, I would recommend that you brush up on that in Volume 1 of the OpenStax Calculus book, Section 4.5. We can also talk about the tangent line, equation of the tangent line at a point. So remember from our Calculus 1 class that the way that we found the tangent of the line, the equation of the tangent of the line at a point, we would have said this is y is equal to m tangent of x minus x1 plus y1, or x naught and y naught if you want, where the slope of the tangent, m of the tangent, we know is the derivative. So we're going to do the same thing here. We're just going to do it with parametric equations. So we first need to find the slope of the tangent. The slope of our tangent line is going to be equal to dy dx. Now that's nothing different than what we had in Calculus 1. But now we're going to do it with dy dt divided by dy dx. That was a terrible d. dy dx dt. It's a dx in the denominator, dt. So I need to find the derivative of each one of these two equations, these two parametric equations with respect to y, or with respect to t. So dy and dt, as you do a du there, I just love the d's. This is going to be equal to, I'm going to take the derivative of 3 the cosine of t. 3 the cosine of t is going to give me 3, and it's going to be negative sine of t. I also need to find dx dt. So here's my x, and the derivative of that is going to be 3 cosine of t. Now, we know that dy dt is dy dx is dy dt divided by dx dt. So this is going to be negative this 3, the sine of t, divided by 3, the cosine of t. And this gives me an answer of negative 3, the tangent of t. Now what we're going to do is we are going to evaluate dy dx, evaluate it when t is equal to pi over 4. So in other words, I have negative, and that's not negative 3, it's just negative tangent, the 3's cancel. So it is going to be the negative tangent of pi over 4. I get my unit circle out from pre-calculus 2, and I find that the tangent of pi over 4 is 1. So this is going to give me negative 1. So I've now found the slope. Check. Now I have to find x1 and y1, or x0 and y0. It depends on how you want to look at it. So I go back to how I defined x. I defined x as 3, the sine of t. So this is going to be 3, the sine of t, which I'm going to evaluate at pi over 4. So this is going to give me 3, the square root of 2 over 2. 3 times the square root of 2 over 2. Similarly, I'm going to get my y1 or y0, or whatever you want to call it. Y. We'll subscript these the same, so it's y1 and x1. And this is going to be 3, the cosine of pi over 4, because that's what t is. And so this is going to be 3 times the square root of 2 over 2. So then my equation of my tangent line, y, is equal to negative 1. That comes from here. That's the slope of the tangent evaluated at pi over 4. X minus 3, the square root of 2 over 2. That's my x1. And then it's going to be plus 3, the square root of 2 over 2, because that's my y1. So y is equal to negative x plus 3, the square root of 2 over 2, plus another one of those. I wanted to write 3 there. I just really like 3 today. So then my final answer is negative x plus 3, the square root of 2. And that's my final answer. Now let's do this again by looking at this one. So for this one, I'm going to do my derivative of each one. Remember, my m of my tangent, m tangent, is dy dx, which is dy dt divided by dx dt. So I'm going to go find dy dt, and I'm going to write this as t minus t raised to the negative 1. That way I can do the power fairly quickly. So then this is going to be 1 minus becomes a plus, t raised to the negative 2. I'm going to do the same thing with dx dt. My dx dt, again, I'm going to write this as t plus t raised to the negative 1, so it makes it easy to do the derivative. And this is going to be 1 minus t raised to the negative 2. So then this is going to be equal to 1 plus t raised to the negative 2 divided by 1 minus t raised to the negative 2. Now when I go to evaluate this, my dy dx evaluated at t is equal to 1, what I'm going to get is I'm going to get 2 in the numerator and I'm going to get 0 in the denominator. If we were in the land of functions, we'd say, oh, well, we know that there's a vertical tangent there, and we would stop. We are not in the land of functions when we're in parametric equations. Well, we could be, but we may not be. So we don't stop there and we say, okay, what we have is a vertical line, which is okay. We can have vertical lines when we're talking about tangents in parametric equations. So vertical lines are of the form x is equal to some number. All I have to do then is find that number. And the way I do that is I do it like I did when I was finding my x1 and my y1. So x is going to be equal to, the way I define x is going to be my t plus 1 over t. So I'm going to evaluate my x when t is equal to 1. And so this is going to be 1 plus 1, which gives me 2. So my equation, x is equal to 2, and that is my final answer. Now, let's look to see when they're asking us to find all the points on the curve that have the given slope. So it's similar to what we did before, except for this time I'm going to tell you what dy dt or dy dx has to be. We have to figure out what the t is that produces that. So once again, I need to find dy, and I wrote x because I really like x, dy dx, which is the dy dt, divided by dx dt. So I need to find dy dt. So this is going to be equal to, I'm going to have the derivative of 4 sine is going to be 4 cosine of t. My dx dt is going to be equal to negative 4 the sine of t. So then I have my dy dt over dx dt is going to be 4 the cosine of t divided by negative 4 the sine of t, which we know is just going to be negative. Sine over cosine is cotangent, so negative cotangent of t. Now, negative cotangent of t must be equal to 1/2. So to figure out where this happens is I find the points in which the cotangent is equal to, the cotangent of t is equal to negative 1/2. Now at this point I can go ahead and take the cotangent inverse of both sides, and I've got t is equal to the cotangent inverse of negative 1/2, but it's not on my calculator. Tangent inverse is. So t is equal to the tangent inverse of negative 2. Remember the relationships between tangent and cotangent. And I'm going to get t is equal to, make sure you are in radians in your calculator when you do this, and you get negative 1.107, and we'll go one more digit, 1. This is in radians. So then I want to know the points on the curve that have the given slope. The thing about tangent, though, and cotangent, it's actually in 2 places in which this happens. If you think about tangent and cotangent, it happens in 2 places in which on the unit circle you're getting a negative number. You're going to get a negative number in this, which is down in quadrant number 4. But you're also going to get the same value as if you were in quadrant number 2. So if you add to your negative 1 point something, add to pi, because everybody likes pi, we also get 2.0344. So there are 2 places in which tangent, or in this case cotangent, is equal to a negative number that's in quadrant 2 and in quadrant 4. Here's quadrant 4, here's quadrant number 2. So now I have to go back and, because I want to know the points in which I have a slope of 0.5. So I have my first set of points, x1, which is going to be equal to, I believe it was 4 cosine, yep, 4 cosine of negative 1.1071. And so that ends up giving me positive 1.788. We'll go with one more digit, 9. I'm going to do the same thing with y1, which is 4 the sine of negative 1.1071, and that gives me negative 3.577, I'll go one more, 8. So my first ordered pair is 1.7889, comma, negative 3.5778. The other location in which I have a slope of 1/2 is x sub 2, and that's what I'm doing for the cosine of the 2.0344, and also my y sub 2, which is 4 times the sine of 2.0344. Now I just want to make a quick note that if you need these to be exact answers, then you clearly wouldn't have done this step here. When it said, hey, let's go ahead and do the tangent inverse of negative 2, which will give me the same answer as a cotangent inverse of negative 1/2. What you would have done is you would have stayed right here in terms of the, move that out of the way. we would have stayed right here in terms of the cotangent, and I would have thought about how I define cotangent. The cotangent of t is the same thing as my x value over my y value. So that gives me -1/2. That tells me that x is possibly -1 and y is possibly 2. Or x is +1/2 and y is -2. Either way, I would have then gone back to the way that I defined our cosine and sine. So my sine of any angle, in this case t, is equal to the y value, which is either 2 or -2, over the radius. So my radius would have been the square root of 4 plus 1, so it would have been 2 over the square root of 5. And then, or negative, it could have been a negative. And then the cosine of t is equal to the 1 over the square root of 5. It could be positive and negative. Now, that doesn't give me t, and that's okay. And the reason it's okay is because the way that I defined my x, I'm just going to do it for x. X is going to be equal to 4 the cosine of t. And we have a replacement for the cosine of t, so I could have just wrote this as 4 the square root of 5. Similarly, I'd have said y sub 1 is equal to, oh, one of these have to be negative. Let's make, bam, that one negative. So then sine, my y is 4 the sine of t, and we have a replacement right here for the sine of t, so I could replace that. So I would have gotten -4 over the square root of 5. Now, if I put these in my calculator, this value and this value in my calculator, I am going to get these two values. So I could have done it exact, or I could get my calculator out. Either way, I have to go back to my pre-calculus 2. If you don't remember, it's chapter 7 in your pre-calculus book. All right, now let's take a look at these next two examples. They're asking us to find the slope is equal to 0, and then when the slope is undefined. So let's go ahead and go right to the derivatives. So we're going to do dy dx. And when I found my dy dx, I'm just going to go right to the answers here for dy dx is going to be equal to, on this one, is going to be equal to -8 the square root of 2. Now you can do the math on your own and get that value of the dy dx. That is, of course, by finding the dy dt, dx dt. Now what I know is this thing has to equal, excuse me, that should be t, not 2, not 2. Has to be t. I need this to be equal to 0, so the place in which this equals 0, obviously, when the square root of t is equal to 0, is only when t is equal to 0. So when t is equal to 0. So now I go ahead and back substitute, because I want to know the point in which I have this slope. It's when t happens to be 0. That means x is equal to 2, y is equal to 2, so the point is 2, 2. And that's my final answer for that one. Let's take a look at my last example of these, where I'm asked to find the location of an undefined slope. So I'm going to find my dy dx, and again I would have done the dy dt divided by the dx dt. And at this point you all know how to do derivatives. What I end up with is the cosine of t over the cotangent, or excuse me, the cosine of 2t. Now I know for it to be an undefined slope, I must be divided by 0, and at most cosine is going to be 1, so let's go ahead and use 1. I could use anything for cosine of t, but we know that, 0 has to be in the denominator, and easy to use 1 in the numerator. So that tells me, if I go back on my unit circle, that the places in which cosine is equal to 0, so the places in which the cosine of 2t is equal to 0 is when my angle, which is 2t, is straight up at pi over 2 or straight down. So let's just do it as pi over 2 plus pi k, because we know that multiples straight up or straight down. So if I take pi over 2 and add or subtract multiples of pi, I'm going to get straight up and straight down on the unit circle, which means I'm going to have a slope of 0. So I really just kind of focused in on this part of it. I want to make sure that that denominator is equal to 0. So then I have t, dividing everything by 2, I'm going to get t is equal to pi over 4. And then I'm going to get pi over 2k. To make my life easy, I'm going to go ahead and make the same common denominator. So t is equal to pi over 4 plus 2 pi over 4k. Now I'm going to start finding values of k. When k is equal to 0, my first one is pi over 4. When k is equal to 1, I put that in there and I get 3 pi over 4. When k is equal to 2, I'm going to get 5 pi over 4. And when k is equal to 3, I'm going to get 7 pi over 4. Now these are my t values. I now then have to go back and put these back into my ordered pairs. So I'm just going to do it for the first one. Remember, my x was equal to sine 2t, so x is equal to the sine of 2t. So evaluating at pi over 4, x is equal to the sine of 2 times pi over 4. Pi over 4 gives me 2 times pi over 4 is pi over 2. So when x is equal to 1. The y was defined as, if you remember, it is this 2 sine t. So 2 sine t. Wait, was there a 2 in front of the other one? There was not. Okay, I just want to make sure. Okay, so then this is going to be equal to 2 the sine of pi over 4, which is going to be 2 times the square root of 2 over 2. So my first ordered pair is going to be 1 comma 2, square root of 2, excuse me, 1 comma square root of 2. And I'd have to do this for each and every one of these, right? So I'd have to do it for this one and this one and this one. So I'll end up in 4 points along my curve in which my slope is undefined. So this is the first point, and then there are 3 other points in which it's undefined. Let's take a look at this one. We want to write an equation of the tangent line in Cartesian coordinates for a given parameter. So they're telling us that our x and y are equal to 1, 1. So our ordered pair x comma y is equal to 1, 1. I still want the slope of the tangent line, so I still want the dy dx, which is still going to be equal to dy dt divided by dx dt. No surprises there. When I do this, I'm going to end up with the numerator by the chain rule is 2t minus 1. The denominator is e to the t all day long. I need to figure out what the t value is to be able to put that in. To figure that out, I know that x is equal to 1, but it is also equal to e to the t. That's coming from here. I know that y is equal to 1, which is also equal to t minus 1, the quantity squared. That comes from here. Now remember, I'm trying to find t. I have my x, y coordinates already. I don't have to do it like in my previous example. I had to find my x, y coordinates. They're giving me the x, y coordinates, but I have to find the t that satisfies this. So focusing on this, the only time that happens is when t is equal to 0 for this. This one, I'm going to take the square root of both sides, and so I get plus and minus 1 is equal to t minus 1. I'm going to add 1 to both sides, and I'm going to get either 2 or I'm going to get 0 for t. Those are my 2 choices by solving for 1 is equal to t minus 1, the quantity squared. The only one that satisfies the ordered pair 1, 1 is when we have t is equal to 0. That is the only one that satisfies it, because it has to satisfy, that t value has to satisfy both the x parametric equation and the y parametric equation to get 1, 1. So now I have my t value, so I'm going to go over here and I'm going to say, let's go ahead and evaluate dy dx. When we evaluate it, we're evaluating it at t equals 0, which is going to give me 2, 0 minus 1, e to the 0, which is going to give me negative 2 over 1, or in other words, negative 2. I want the equation of the tangent line, and I just found the slope. So then y is equal to negative 2, x minus my x1 right here, plus my y1, which is right here. And so I've got y is equal to negative 2x plus 3, and that is my final answer. Now, let's take a look at second order derivatives. We know from Calculus 1 that the second derivative, d2y of dx2, is the derivative of the first derivative, right? But since we know that dy dx, this dy dx, is dy dt, dx dt, then we know that this numerator becomes the derivative of the derivative with respect to t over dx dt. So here is a very, very useful, handy formula that I don't give to you on the test. So make sure you have practiced it enough that you have it down. So let's go ahead and do this last derivative, and then we'll start integrating. So when we start to do the derivative here, I first need to find my dy dx, which is still the dy dt over dx dt. So by the product rule and chain rule, we're going to have e to the 2t plus 2t e to the 2t in the numerator, and in the denominator we're going to have e to the negative t. Now I'm just going to clean this up algebraically, and so I get e raised to negative e raised to the 3t minus 2t e raised to the 3t. That gives me my first piece. Now remember, it is d dt of dy dx, dy dx, dy dx in the numerator, and then it is the dx dt in the denominator. So now I'm going to take the derivative of this. So I'm going to do d dt of this, which is negative e raised to the 3t, minus 2te raised to the 3t. So this is going to be equal to negative 3e raised to the 3t by the chain rule. Now I'm going to have to do the product rule, and so the derivative of negative 2t is just negative 2e to the 3t. And then the derivative, excuse me, of the e to the 3t is going to give me negative 6 te raised to the 3t. Now I can combine up some of these terms and I get negative 5e raised to the 3t and negative 6te raised to the 3t. So that was my second step. My third step is I'm going to go ahead and bring this together with the dx dt. So I'm now ready to say d2y of dx2 is going to be the negative 5e raised to the 3t minus 6te raised to the 3t divided by the derivative we have right here. So divided by negative e raised to the negative t. Again, I'm going to clean this up like I did before. I end up with a positive 5e raised to the 4t and then a positive 6te raised to the 4t. And that is my final answer. Cool, 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 cool. So let's take a look at integrating. Now, provided my parametric curve does not cross itself, then the way in which I find the area underneath the curve is defined here, where I have y of t, that's a parametric equation of y with respect to t, and then the derivative of the parametric equation of x with respect to t dt. I may or may not have these a's and b's, but these a's and b's are in terms of t. It is not in terms of x and y. So if I'm asked to find the area under this curve, then I need to find y prime. I need x prime of t. X prime of t in this case happens to be negative sine of t. So I now have the integration of my y of t, which is e to the t. I'm going to put the negative out there, and then the sine of t dt. What I don't have is my a and my b. So I'm going to have to figure out what my a and my b is. I have to figure out what t is, just like I did before. So I start with the fact that x is equal to 0, but x is also equal to the cosine of t. So I focus in on this part of it, and it says, oh, look, cosine of t equals 0 when t is equal to pi over 2 or 3 pi over 2. Now, because of the fact that they're telling me that I am only going to restrict myself between 0 and pi over 2, then I have my first t. I don't know if it's A or B, so I have to go look at the next one. So I have y is equal to 1, which is equal to e to the t. Now, if I focus in on this part, then I know the only time that happens is when t is equal to 0. So my upper bound is going to be the larger number, and that's going to be the pi over 2. My lower bound is going to be the smaller number, and that's going to be 0. And now I'm going to integrate this, and I'm going to integrate this by parts. So if you remember, the integration by parts is going to be the u v minus integral of v du. So I just have to make sure I get the right u's and v's. So I'm going to choose u to equal negative sine of t. That means du is equal to negative cosine of t dt. My v is equal to e to the t, and then, my dv dt, still going to give me the same thing, but my dv dt is e to the t dt, and then my v is equal to e to the t. Okay, so we come back here. So I have negative sine of t multiplied by e to the t. And then I have minus the v, which is e to the t. And then my du, which is negative cosine of t dt, which gives me the sine. I'm going to actually write e of t first because I just like it first. So e of t, the sine of t, don't forget your negative, I wanted to drop it, plus the integral of e of t, the cosine of t, dt. And you're thinking, what? And I'm thinking, oh, look, we get to do this again. So we have to do the integration by parts yet again. So if you remember from when we were doing this before, we had to do the integration by parts. And so we would do this part again. And we would have ended up with something like this. We would have had, by integration by parts the second time, we would have had negative e of t, the sine of t. That looks like something else, like it shouldn't be. Being lazy, stop that. Okay. Plus e of t, the cosine of t, plus the integration of e of t, the sine of t, dt. Now remember, what I started out with way over here was, I started out with integration of negative e of t, the sine of t dt. So if you remember from integration by parts, when this happens, when I start to cycle through, then I go ahead and move this to the other side, and so I get negative 2, because I now have 2 of them, e of t, the sine of t dt is equal to negative e of t sine of t plus e of t, the cosine of t. Now if I divide everything by negative 2, then I get my final answer, which is, when I divide by negative 2, I'm going to get 1/2 e of t. I'm just going to factor out a negative e of t so that when I divide by 2, I don't have to worry about anything else. And then I get the sine of t. And then, let me see, when I factor that out, that's going to be a minus the cosine of t. Now let's go ahead and finish this off. Let's evaluate this from 0 to pi over 2. So we're going to put pi over 2 there, and so we get 1/2 e, 1/2, not, I was just excited about e, 1/2 e raised to the pi over 2. The cosine, the sine of pi over 2 is 1. The cosine of pi over 2 is 0. And then minus 1/2, again with the e. I say 2, and I write e. So 1/2 e to the 0, and the sine of t is 0, the cosine of 0 is 1, and so my final answer is something of the form e raised to the pi over 2 minus 1 all over 2, whatever that happens to be in my calculator, but there's the exact. Let's take a look at our next example. They're asking for the area underneath one arch. Now, if you remember, these are of the form of a cycloid, which is basically like a wheel going around on the road, if you will. And so that tells me that if it's a wheel, I must be going from 0 to 2 pi. So my integration is from 0 to 2 pi. This is from section 1.1 when we talked about cycloids. It is of the form x of t is equal to a, some a value out front, and then t minus the sine of t, or in this case theta, it's fine, and y of t is equal to a, and then 1 minus, or excuse me, yeah, 1 minus the cosine of t. In this case, it's theta again, it's still fine. So we know that this is a cycloid. So we know that it's going to go from 0 to 2 pi because it's going to go the circumference of my circle to have an arch. If you're not certain, go take a look in section 1.1. Anyways, we need to find x prime. X prime of theta, which is going to be the r. R is just a constant, and then the variable is theta, so the derivative of theta is 1, and then minus the derivative of sine of theta, which is going to be the cosine of theta. So then this is going to be my y of t, which is going to be r, 1 minus the cosine of theta, multiplied by 1 minus another cosine of theta, and it is d theta. Now remember that my t can take on any variable. Just because it's theta does not mean it's not a parameter. So we know that, oh, I forgot my r there. Don't forget my r, so r. So I have r squared. I'm just going to pull that out because of the fact that it is just a constant. So I'm just going to pull that out. And then what I end up with is 1 minus the cosine of theta, the quantity squared d theta. What I'm going to do, because it's going to be easier to just integrate it using regular integration rules, is I'm going to go ahead and expand this out. So I have r squared, the integral from 0 to 2 pi. And when I integrate, when I multiply this out, I'm going to get 1 minus 2, the cosine of theta plus the cosine squared of theta, d theta. Now you're thinking, wait a minute, she said it's going to be easier. It is, if we remember that we're going to use the power reduction rule on that. So using the power reduction rule on that, we're going to end up with r squared from 0 to 2 pi of 1 minus 2 cosine of theta. My power reduction rule is 1/2 minus 1/2 the cosine of 2 theta. So that is the power reduction formula. So if you don't remember that, please go take a look in your Pre-Calculus 2 book. And then d theta. Now this is much easier to integrate now. So when I go to integrate this, I'm going to get r squared. I'm going to integrate the 1. That's going to give me theta. And then minus 2. I'm going to integrate cosine, and I get sine of theta. And then, oh, I should have added the 1/2 and the 1, so let me do that. So I'm going to add these two, which gives me 1/2 and 1 is 1.5, or 3 over 2. So 3 over 2 theta. And then I have minus this 2, the sine of theta. And then when I integrate the negative 1/2 cosine of 2 theta, I'm going to end up with negative 1/4 the sine of 2 theta. I'm now going to evaluate this from 0 to 2 pi. And once I evaluate this from 0 to 2 pi, my final answer ends up becoming 3 pi r squared. So that is my final answer, and it is the area underneath one arch of the cycloid. And this is going to hold true for any cycloid, whatever your radius is. So we found it generically. Cool. Cool, cool, cool. Let's go ahead and look at the arc length of a parametric curve. Arc lengths are going to be really, really similar to the way that we found arc lengths before. We know that the arc length from before had the derivative, and if you want to refresh your arc length, it is in Calculus Volume 2 book, and I believe it's in like Chapter 2. We're going to use this formula, which says I need to know my T1 to T2, which thankfully they give me. Here's my T1 and here's my T2. So then all I have to do is just use this formula, which is I need to find the derivative of each one of these, my dx dt. My dx dt is going to be -2 the sine of 2t. My y dy dt is going to be equal to 2 the cosine of 2t. So then all I have to do is find the arc length s, which is equal to, from 0 to pi over 2, the square root of my dx dt, the quantity squared, so -2, the sine of 2t, the quantity squared, and then plus 2 the cosine of 2t, the quantity squared, dt, from 0 to pi over 2. And then I'm going to have the square root of 4 the sine squared 2t plus 4 the cosine squared of 2t dt. If I factor a 4 out, I'm going to have the integration of 0 to pi over 2 of the square root of 4, which is 2. And then I have the sine squared of 2t plus the cosine squared of 2t. But we know that the cosine squared plus the sine squared, so the sine squared of any angle plus the cosine squared of any angle is equal to 1. That means this lovely, which looks like it would have been nasty to integrate, is just 1. And so I have 0 to pi over 2 of 2 dt, which is just equal to 2t integrated from 0 to pi over 2, which just gives me pi. We all like pie. Pie is delicious. And that's it for that one. Not bad. Looked like it was going to be bad. It really wasn't that bad. Now, similarly, I'm going to find the surface area generated by the parametric curve, and it's going to be similar to what I had before. Notice I still have my derivative of x with respect to t, the quantity squared. My derivative of y with respect to t, the quantity squared. The only thing that's different is this value out front, which is the derivative of y. And of course, we have this 2 pi. So if we are asked to find the, the surface area by rotating this, the first thing I'm going to do is find my derivatives. It's always finding my derivatives. We always go back to the derivatives. So when we find the derivative, I have theta, so this is our t or theta, whatever. So we have x prime of theta is equal to -3a, because a is just a constant, the cosine squared of theta, and then multiplied by the sine of theta, because it's the chain rule. And then y prime of theta is going to be something similar. It's going to be 3a, the sine squared of theta multiplied by the cosine of theta. Now we're going to go ahead and plug that in. So we have from 0 to pi over 2 of 2 pi. And that is y of t, not y prime of t up there. So y of t, which is going to be a, the sine cubed of theta, the square root of. So I notice that there's a 3 common in both and there's an a common in both. So I'll end up with having an 9a squared. So they're going to be common in both. And then I'm going to end up with squaring the first one, which is going to give me the cosine raised to the 4th power, the sine squared. Don't forget your theta and the theta. Plus the sine to the 4th of theta, the cosine squared of theta, and d theta. And you're thinking, oh, this is going to be awful. Well, actually, it's not that bad. It's not great, but it's not bad. So what I'm going to do out of this is I notice that the highest power I can pull out is a sine squared. And the highest power I can pull out on cosine is cosine squared. So if I pull out a sine squared and a cosine squared from each one of those terms, I'm going to end up with the cosine squared of theta plus the sine squared of theta. Now, what I have now is a string of multiplications. I have 9a squared and the square root of all of that. So I can take the square root of each one of those factors individually. So I end up with 2 pi from 0 to pi over 2 of an a is going to be, the square root of a squared is going to be a, so that's going to give me a squared, and that's because I had an a already. And then I'm going to have the sine cubed of theta. Oh, don't forget that 3, the square root of 9 is 3. And then I'm going to have, when I do the square root of sine squared, it's going to give me just another sine theta. And then I'm also going to get a cosine of theta when I take the square root of cosine squared. And we know that cosine squared plus sine squared is equal to 1. And so that's where I am. So it seems like it was terrible, but it wasn't that bad. Now I'm just going to clean this up just a little bit more. And I'm going to have 6 pi a squared, because those are all constants, from 0 to pi over 2 of sine to the 4th theta cosine theta d theta. And if I do u substitution and say let u equal the sine of theta, then du is going to give me the cosine of theta. And so what I have is 6 pi a squared is going to be divided by 5, and it'll be the sine of theta raised to the 6th power, or the 5th power. Sine raised to the 5th power of theta, evaluated from 0 to pi over 2. And so my final answer is simply going to be 6 pi a squared divided by 5, because the sine of 0 is 0. The sine of pi over 2 is 1. So there's that one. Let's take a look at my last example here. This is kind of a long video. We are going to, I guess I should have talked about it going around the x-axis. This is all revolving around the x-axis. So now we're going to revolve around the y-axis on this one. And because we're revolving around the y-axis, the thing that changes on my formula up here, let me just erase this. The thing that changes in terms of my surface area if I'm going around the y-axis is going to be 2 pi from A to B. And now it's going to be x of t here. And then the square root, and everything else is the same. But because I'm going around the y-axis, my parametric equation I use here is x of t, not y of t. Just as a heads up. Okay, same thing. We're going to find x prime of t, which gives me 2t. I'm going to find y prime of t, which is going to be 4t. Now, I know my limits of integration, so this is going to be 2 pi from 0 to 1 of t squared, because that is my x of t, the square root of 2t, the quantity squared, plus 4t, the quantity squared, dt. So 2 pi evaluated from 0 to 1 of t squared. Inside, I'm going to get 4. 2 squared is 4. And then 4 squared, which is 16. So I'll end up with 20. And it'll be t squared dt. I'll go ahead and take the square root. And so I have 2 pi. The square root of 20 is not going to do anything, but it is a constant, so I can pull that out. The square root of 20 can come out. from 0 to 1. And then I'm going to have t squared. And the square root of t squared is another t dt. And so I end up with 2 pi square root of 20. T to the third, when I integrate it, is going to give me t to the fourth divided by 4. I'm going to evaluate it from 0 to 1. That should be 20. It's a terrible looking 20. That was terrible looking 20. So my final answer when I get done is going to give me pi square root of 20 over 2. But the square root of 20 is the same thing as the square root of 4 times 5, square root of 5. So let me just write that as square root of 4 is 2, square root of 5 over 2, which just gives me the square root of 5 times pi. And that is my final answer. And that's it for this video.